When we were doing our simple example of the finite element method, we've seen that you can write the energy in a certain element. So let's call that element, for example, the first element, that you can write that as a quadratic form as follows. So we have the fields at the edge of our elements. Let's call those psi1 and psi2. And then we can write that as a matrix, A1, B1, C1, D1, which we multiply on both sides as follows. You can also write down a similar expression for the energy in the second element, which is next to it. Let's call the fields there in the disconnected numbering scheme psi3 and psi4. That element will also have an ABCD matrix of its own, which we call A2, B2, C2, D2. And then we can complete the equation as follows. So this is how we can write the energy in a matrix form for each of the individual elements. The question is, can you now also write the total energy as a bigger matrix? So pause the video and think about how you would do that. The total energy is, of course, the sum of J1 and J2. And obviously, if you have more elements, you can do that in a similar fashion, but I'm only using 2 here because the pattern will become clear soon enough. And that you can actually write as a bigger matrix involving blocks. So for example, you can write this as a row vector, psi1, psi2, psi3, psi4, times a much bigger matrix, A1, B1, C1, D1. And then in the top right, we have zeros everywhere. We also have zeros everywhere over there. And then we have A2, B2, C2, D2 over there. And then we have a much bigger column vector, psi1, psi2, psi3, psi4. And you can easily verify that elaborating this expression here is exactly the same as just summing the 2 expressions that you have up there. For example, you could make use of block matrix multiplication to simplify this. So for example, rather than saying that this is a 1/4 vector, you just combine those into blocks such that this becomes then a 1 times 2 block matrix. And then you also have blocks over here, which is then a 2/2 block matrix. And if you do the multiplication of these first 2 guys, if you multiply this thing by that thing using block matrix multiplication, so what's going on first of all is you multiply this thing by that thing over here, and then you have the sum with the multiplication of that thing by that thing, which is 0. So you only have this multiplication for your first column. So if I just quickly copy that, psi1, psi2 times our first ABCD block, A1, B1, C1, D1, okay. And then we do that for the second column. So for the second column, we first have this times this. So this is 0 plus that times that. And that's then psi3, psi4 rather. Psi4, the second ABCD matrix, A2, B2, C2, D2. And then we have psi1, psi2, psi3, psi4, which actually should also be considered as block matrices here. Block vectors, rather. So now we have a 1/2 times a 2/1. So if you multiply that out, you multiply this thing by that thing plus that thing by that thing. And that's just summing these 2 things, which is indeed what you should show. If you're not convinced by this block magic of multiplication here with using block vectors and block matrices, then you just do it the hard way. Not with blocks, but with individual row and columns. And then you can easily verify for yourself, for example, for the first column, that what you should do is first psi1 A1 times psi2 C1 you get, and then you get exactly the same thing if you do that for that equation over there. my arm is a bit too short, but you have then psi1 A1 also plus psi2 C1. So you can easily verify that column by column. This gives you exactly the same result. So this is how you can write the total energy then as a block diagonal matrix.